What if I told you that one of the biggest problems in cloud computing could be solved by thinking about ski rentals? Every day, cloud databases face a hidden trade-off. Keep more data in memory for speed, and you waste money on idle resources. Keep too little, and performance drops when users need it most. This is the Goldilocks problem of caching, finding the perfect balance between cost and speed. In this video, we'll explore linear elastic caching, a smarter way to make cache memory adapt in real time. We'll look at why static cache limits fail, how the classic ski rental problem connects to cloud systems, how TTL prediction helps decide what data stays or leaves, and how this idea can reduce cost while maintaining performance in systems like Spanner. So the big question is, are today's cloud systems built for static limits or real-time reality? Let's get into it.
Welcome to this explainer. Okay, today we are tackling a subject that sits at the absolute heart of modern digital infrastructure. We're going to demystify a highly complex and, honestly, incredibly expensive challenge in database memory management. Look, if you operate at any kind of scale in the cloud, you already know that speed is everything, but that speed comes with a massive hidden financial burden. So today we're looking at some absolutely fascinating research from Google that fundamentally reimagines how we pay for and allocate memory.
But hey, before we dive into the heavy technical architecture, I want you to consider this kind of unexpected question. How does a classic winter vacation dilemma solve a multi-million-dollar cloud computing problem? It sounds totally like a riddle, I know, but by the end of this explainer, you are going to see exactly how a simple choice you might make on a snowy mountain is actually unlocking massive cost savings in globally distributed databases. So keep this question right in the back of your mind.
Section 1. The high cost of speed and the hidden price of lightning-fast apps. To really understand the solution here, we've got to understand the problem. Modern high-performance databases are under immense pressure to deliver lightning-fast response times. We all expect our apps to load instantly, right? So to achieve this, systems rely heavily on in-memory caching. They stash frequently accessed data in RAM so they can completely bypass those slow, cumbersome disk operations. RAM is incredibly fast for sure, but there is a major catch.
$3. I mean, it doesn't sound like much, right? But this is the daily cost for just one single gigabyte of serverless memory in some cloud providers. 1 gigabyte. Now, imagine running a globally distributed database, processing billions of requests every single second. You aren't dealing with 1 gigabyte. You're dealing with terabytes, maybe even petabytes of memory. That $3 scales up exponentially into an absolutely massive, agonizing daily expense. High-speed memory is quite literally one of the most expensive resources in computing.
Section 2. The Goldilocks cache problem and finding the perfect fit. Historically, managing the super expensive cache has basically been treated as a rigid, static guessing game. Engineers just kind of guess the static limit for their memory allocation.
It's the classic Goldilocks dilemma. On the one hand, if you size your cache too small, your system is constantly running out of space, which forces slow disk fetches that absolutely tank your app's performance. But on the other hand, if you size it too large, just to handle those rare traffic spikes, you waste incredible amounts of money on idle memory that just sits there doing nothing most of the day. You are essentially paying top dollar for empty space.
The Google researchers actually perfectly captured the reality of this. To quote them, "Sizing the cache too large for peak demand wastes thousands of dollars on idle memory. That is a literal financial sting. Relying on traditional fixed-size eviction policies like least recently used, or LRU, means you're always trapped between terrible performance and terrible economics. It's like you can never get it just right."
Section 3. The ski trip dilemma. Renting versus buying. All right, we are going to completely reset our perspective for a second and head to the mountains.
Picture this. You're on a ski trip, but you have no idea how long it's going to last. Every single morning, you face this dilemma. You can rent skis for a small daily fee, or you can bite the bullet, buy the skis for a huge upfront cost, and then ski for free every day after that. If you knew you were staying for exactly 10 days, well, the math is easy, but you don't know. Without knowing the future, you need a mathematical algorithm to decide whether to keep paying a little each day or take that big upfront hit to minimize your total spend. Now let's map this directly onto cloud memory management, because this is where the real breakthrough happens. Every piece of data faces this exact same dilemma. Keeping data in fast RAM is exactly like renting skis. You're paying a continuous, small cost.
Evicting the data to save space is like deciding to buy. You risk a massive buy cost in severe latency and I/O penalties that you'll suffer if you need to fetch that data from the slow disk again soon. Section 4. Linear Elastic Caching Explained. Memory as a Dynamic Utility. The crucial aha moment here is that memory shouldn't be a fixed box. Instead of a pre-allocated bucket, the Google researchers proposed treating memory as a dynamic utility. The cost is linear, and it's based on both the size of the cache data and the exact duration it's held in the cache.
To make this work, the algorithm relies on time to live, or TTL. Simply put, this is the specific duration assigned to a piece of data to remain in the cache before it's automatically evicted. Going back to our analogy, TTL is exactly your ski rental duration. You decide up front how long you're willing to rent the space for that specific piece of data. If it isn't accessed again before its TTL expires, boom, it gets evicted.
So how do you predict the perfect TTL for millions of pieces of data in real time? Well, first, the system analyzes specific data access patterns and the exact cost of a cache miss. Second, it feeds this into a highly efficient, super lightweight decision tree written in just a few lines of C++ code. Because a system like Google Spanner handles billions of requests per second, this literally cannot be a heavy AI model. Finally, it instantly assigns the optimal TTL to that data page. It optimizes that rent versus buy decision for every single piece of data individually. It's brilliant.
Section 5. Real-world cloud economics and putting the theory to the test. Theories are great, right? But do they actually survive reality? Well, the researchers integrated this policy directly into the production servers of Google Spanner, which is one of the largest, most heavily utilized distributed databases on the planet.
The results they achieved over several months were honestly staggering. They saw a 15.5% reduction in memory usage. That is a massive volume of expensive RAM freed up. Now, you will notice cache misses did increase slightly by 5.5%, but here is the genius of the algorithm. Because it's cost-aware, it concentrated those cache misses only on data that was incredibly cheap and fast to fetch from storage. That means the actual impact on I/O cost was a negligible 0.5%. Ultimately, all of this drove a 5% reduction in the total cost of ownership. And let me tell you, at Google scale, 5% is an astronomical amount of money.
Now, you might be thinking, okay, this only works for Google's crazy proprietary infrastructure. But actually, the researchers rigorously tested their elastic caching against publicly available cache traces from standard industry benchmarks. They pitted it directly against an optimized implementation of a fixed-size baseline policy known as GDSF.
And the final outcome is definitive. When comparing total costs at high capacity, the traditional fixed policy sees its total costs absolutely soar because you're forced to provision massive amounts of idle memory. But with Elastic Cache, because it dynamically adapts to the real-time workload, releasing memory when it's not needed and renting it exactly when it is, the total cost stays remarkably low. It scales so economically.
So we've seen how framing memory as a ski rental problem can literally save millions. By shifting away from static peak load guessing and moving toward a dynamic, cost-aware model, we can build systems that are blazingly fast and economically lean. So I'm going to leave you with this final thought to chew on. Is your infrastructure built for static peak limits, or is it actually adapting to real-time reality? Because in the era of cloud economics, paying for empty space is a luxury no one can afford. Thanks so much for joining me for this explainer, and I'll catch you on the next one.